Now, when you do work with a machine, we need to think about something called efficiency. You need to look at work input, which is the work or energy that you supply to the machine to make it go, and the work output, which is the work or energy that comes out of the process, what the machine does for you. The efficiency of a machine is defined as the ratio of work output divided by the work input. And to make it a percent, which is what efficiency is, you're going to multiply it by 100 after you divide the work output by the work input. Another way to think of work output is work done by the machine, and another way to think of work input is the work that you did to make the machine work. Machines are always going to be less than 100% efficient because of friction and other transformations of energy that don't involve the energy actually going into the machine working. For example, when friction turns energy into heat, that heat is not doing work for you, and so that's why your efficiency drops. Cars are notoriously inefficient because most of the energy in the gasoline of a car is wasted as heat. They're also inefficient for other reasons like friction, the car running but not actually going anywhere. It's called idling. All the electronics and things in a car that work and need energy to work. And that leaves you with a very small amount of energy that's actually being transformed from the stored chemical energy in the gasoline to the energy of the car applying a force through a distance and moving. We actually talked in Chapter 7 a little bit about energy and efficiency and conservation, and here's another example. Light bulbs are taking energy from electricity and turning it into energy of light. At least that's the purpose of a light bulb. Traditional incandescent light bulbs are very inefficient at that. They take a very small percentage of the electrical energy and turn it into light energy. Most of it is actually wasted as heat. So that's why more modern and efficient light bulbs like fluorescent or LEDs get much better efficiency, and they also, if you touch them, they get a lot less hot. Let's look at a couple sample problems for efficiency. So say you do 100 joules of work on a lever. The lever does 90 joules of work. What's the efficiency? This is the most basic problem you can have. The work that the machine does, 90 joules, divided by the work that you do, 100 joules, multiply it by 100 to make it a percent, it's 90% efficient. Another way to think of efficiency is it's the grade of the machine, right? Like you get a 9 out of 10 on a quiz, you got a 90%. This machine did 90 joules of work, but you were expecting 100 because that's what you put in, 90% efficient. Here's a second sample problem. A pulley lifts a 10 Newton weight 1 meter. You pull on the rope with a force of 5 Newton and you pull the strings 2.5 meters. What's the efficiency? So here we have two forces and two distances, and with that we're going to figure out the work done by the machine and the work done by you. The machine applies a 10 Newton force over 1 meter, so it does 10 joules of work. You, however, applied a 5 Newton force over 2.5 meters, so you did 12.5 joules of work. Please note, you did more work, but your work was probably easier because you were pulling with less force, and that's the advantage of using a machine. It lets you do things easier, not with less work. So the efficiency is the output divided by the input. The machine does 10 joules, you do 12.5, so the efficiency is 80% efficient. And that's it for energy, efficiency, work, and power.